So yesterday we started with coordination compounds. And today we are going to go further to see how we are going to calculate how we know the charge of a complex, or how to calculate the charges, the coordination numbers, and the geometries based on what we learned yesterday. And I know that yesterday we also looked at how to get the charge of a complex. We just did a brief of that yesterday. So today we are actually going to do some calculations. I hope we are there with our notes. So what are charges? Just as I've told you, a complex ion is a coordination compound that has a charge. So the charge of a complex is the sum of the charge on the central metal and on the surrounding ligands. So for you to know the charge of a complex, you must be able to know the anionic ligands, the sum of the anionic ligands surrounding the metal. So, and in doing that, we should be able to determine the oxidation number of the metal. And if we determine the oxidation number of the metal, then we should be able to know the charge of the complex ion. So we have an example there. I have one example there. Your tetraammonium copper 2 sulfate. Now, you are given this complex. We want to know what is the oxidation state of copper here. So I've done the calculation. Because we are looking for copper, we call copper X plus ammonia. I told you ammonia is a neutral ligand, which is 0. The charge is 0 multiplied by 4 plus your SO4. The charge on your SO4 is 2 minus. So that is how we got this 2 minus. So, and the total charge of every complex always equals 0. So we have X plus, this is already 0, minus 2 is equals to 0. So X is equals to 2, and X is our copper. So invariably, the oxidation state of our copper is plus 2. So the oxidation state of copper is plus 2. So the next, we also have our copper. We also have our copper coordinated to 4 ammonium ligand, and now it has a charge. It has a charge. So we are also going to determine the oxidation state of our copper. So for the one that has a charge, the total number of charge on this complex is now going to be, instead of 0, it's now going to be plus 2. So we have our copper as X plus, this is already a neutral ligand, which is 0, is equals to 2. So that instead of 0, if there was no charge here, it would have been 0. But because we have plus 2, then the total number of charge is 2. So the oxidation state of copper here is also 2. Now, the next one is our rhodium complex. For our rhodium complex, we are looking for the oxidation state of the metal, which is our rhodium here. So our rhodium is X. Our ammonia here is 0, so 0 times 5 plus our chlorine, our chloride ion. Of course, you know the oxidation state of chlorine is -1. The charge is -1. And our NO2 is also -1. So we have plus -1 plus 2, because there's 2 here, multiplied by the charge in this NO2, which is -1. So because it has no charge, it's neutral, so the total number of charge is equals to 0. So we have our X plus 0 minus 1 minus 2 is equals to 0. So our X is 3. So invariably, the oxidation state of your rhodium in this complex is 3 plus 3. So that is actually how to determine the oxidation state or the primary valency of any complex. Now, aside determining the oxidation state, we can also determine the formula of a complex. How do you determine the formula of a complex? We can determine that by the number of molecules and the ions involved in coordination. The number of molecules, that is the number of the ligands, and the number of either the neutral ligands or the ionic ligands. So this is an example. I gave an example here that if a complex ion contains chromium 3, so chromium 3 bound to 4 molecules of water and 2 chloride ions, what is the formula of the complex? So now I have told you it's chromium 3. The chromium is oxidation state of 3, and it has 4 water molecules, and it has 2 chloride ions. So what is the formula? So what is the formula? So we already know that our chromium is +3. Our water is neutral, so 4 times 0 plus our chloride ions is -1 times 2 is equals to 0. So what invariably, your complex will have a charge of +1. So this is our chromium with 4 molecules of water, 2 molecules of chlorine. And because we have calculated the charge, so it's not a, so whatever, so this complex, of course, we've already seen that it's a complex ion. If it was just a complex, then we won't expect any charge. But because the question says it's a complex ion, we want to know that ion, is it a +1? Is it +2? Is it -1? Is it -2? What is the charge on that complex? So from our calculation, we have seen that the charge on the complex is a +1. So, and I give a little question here. It says, what is the charge of the complex formed by platinum-2 metal ions surrounded by 2 ammonia molecules and 2 bromide ions? Can we do that and give me the answer in the next 1 minute? Can you hear me? Can you all hear me?
Yes.
So I gave a question now. Can you do that question? What is the charge of the complex formed by a platinum-2 metal ion surrounded by 2 ammonia molecules and 2 bromide ions? Did we understand what I just explained?
Yes, ma'am.
Having a lecture. So can we do that calculation and let's have the answer?
0, ma'am. 0.
It has no charge, isn't it?
Yes, ma'am.
Good. So that shows that you understand what I did. So that for this particular complex, it has no charge. So we are going to have a platinum, ammonia is how many? 2, and our bromide is 2. So with no charge. Thank you. So that is how to calculate oxidation number, and also using the oxidation number to know if the complex will be charged or the complex will not be charged, depending on what you have calculated. So you can be given the complex and you are asked to calculate the oxidation number, or you can be given the equation and you'll be asked to write the structure. So either way, you should be able to know the structure of the formula of the complex, and you should be able to know if it's charged or if it's a neutral complex. So we now look at coordination number and geometry. We've already discussed what coordination number is. Coordination number is the secondary valency. Coordination number is the secondary valency, and that is actually talking about the ligands that surrounds the metal ion. That is your coordination number. But I want you to note one thing. When we talk about coordination number, we are not really talking about the ligand, because what is directly bonded to the metal is the donor atoms. Yes, we have the metal at the center. So let me just use to explain to you. So I will stop my sharing and we'll go to the board. So if we have this complex, we have let's say I have your cobalt bonded to NH3, bonded to another NH3, let's say bonded to chlorine and bonded to, let's say, another NH3, dependent. So now we already know that this is a coordination compound. And of course, the coordination number of our metal here is 1 + 1, because these are neutral ligands. Now, for us to be able to know what the coordination number is, we know that the coordination number for this particular ligand is 4, because we have 4 ligands. They are talking again. Is that disturbing my class? We know that we have 4 ligands, but the coordination number is 4. But how do we know the donor atoms we are going to look at? The donor atoms for NH3 is nitrogen, because it is your nitrogen that is donating its lone pair to your carbonyl, to your cobalt. So when you talk about the coordination number, we're actually talking about the donor atoms. For every ligand has a donor atom. Every ligand has a donor atom. Why am I disturbing my class? So every ligand, this is a ligand, and the donor atom is nitrogen. Nitrogen is the donor atom. For your chloride, the donor atom is your Cl, because it's just a compound. It's just we just have our chlorine ion. So the donor atom is your Cl. But for your ammonia, the donor, because there are 2 compounds, is nitrogen that is the donor atom. So that is what we mean by coordination number. So the coordination number is the number of donor atoms, not ligands, directly bonded to the metal ion in a complex. So it's not the ligand, it's actually the atom that is making the donation. So it's the number of donor atoms that is making the donation. So donor atom is the atom that is directly bonded to the metal. That is why I have used the board to give that example. So for this, the donor atom here is going to be nitrogen. The donor atom for this complex is nitrogen. So nitrogen is the donor atom. So silver ion has a coordination number of 2. Of course, for this, the coordination number is 2. For this, the coordination number is 1. And for this, the coordination number is 1, 2. It's 2, sorry, because it's going to be equals to 1. So the coordination, so your silver ion has a coordination number of 2 and oxidation state of 1. So the oxidation state of this complex is 1, while the coordination number is 2, because you have 2 donor atoms, 2 nitrogen bonded to your silver. I don't know why this is. So for this, for your zinc cyanide, the oxidation state is +2 for your zinc, and the coordination number is 4. But the coordination number here, because we have your Cn, is not nitrogen. Your zinc is bonded to the carbon. Your cyanide is Cn, not Nc. So the carbon is the donor atom, while the coordination number is 4. Hello, Sheriff. I'm in the office. I'm having a lecture. You can come. Thank you. So for your cyanide, the coordination number is 4 because we have 4 carbon bonded to the zinc. So not the donor atom. The donor atom is not the ligand. The coordination number we are talking about, yes, we are talking about the ligand, but it's the donor atom because it is the donor atom that is actually coordinated to the metal. So the donor atom is 4 and is carbon, while your oxidation number is +2. Likewise, for your platinum, the donor atom is your Cl. Your Cl, that is chlorine, chloride ion. It's not C and it is not L. Is the Cl that is the donor atom. Your Cl is the donor atom. The coordination number is 6. That means Cl is bonded to your platinum and the oxidation state is 4. So it's going to be 6 minus 2, which will give us platinum 4. So for the complex below, give the donor atom, the coordination number, and the oxidation number. Can we do that immediately for this particular complex? Can you hear me?
Yes.
So
Yes,
for
ma'am.
this complex, give the donor atom, coordination number, and oxidation. Can we do that for this complex? What is the donor atom?
The donor atom is the nitrogen, ma'am.
Good.
Nitrogen.
What is the coordination number?
6.
6. What is the oxidation number?
+2, ma'am.
+2. So good. So that shows that you understood what we're talking about. So
It's from here.
What is your
John, you're talking about relationship.
can we stop talking, please? Can we keep quiet? So the most common coordination number are usually 4 and 6. It's usually 4 and 6, although some can exhibit constant coordination number, just like your chromium. Your chromium 3 and cobalt 3 is usually exhibit coordination number of 6, while platinum is always 4. We see that the common ones are 4 and 6, but some can exhibit constant coordination number. Example is chromium 3 and cobalt 3. You always exhibit coordination number of 6, while platinum is always 4. Also, the coordination number, that is the number of ligands, that is donor atoms, bonded to the metal ion can actually vary. What will make it to vary will depend on the size of the metal ion and the surrounding ligands. What do we mean by that? That will depend on the kind of ligand. If they are large ligands, if the ligands are large, or the ligands are small. For example, we have the fluoride and the chloride ligand. Both of them are bonded to iron. So both of them are iron 3. But now we see that the first one, the fluoride, is having 6, while your chloride is having 4. Why? Because your fluoride ion is smaller. So because it's smaller, it can contain more than your chloride ion, which is larger. So with larger ligands, fewer number of ligands will coordinate to the metal ion. So the smaller the ligand, the more of those ligands that will coordinate to the metal. The larger the ligand, the fewer number of ligands that can coordinate to the metal. So these are some of the factors that can affect the number of ligands that can coordinate to your metal. Also, ligands that transfer negative charge to the metal produce lower coordination number. Example, your anionic ligands and your neutral ligand. Your anionic ligand, because they are going to transfer more charge to the metal center, the metal center will coordinate less with such ligand. Unlike your neutral ligand, which they are not transferring any charge to the metal, so your metal can coordinate more of the ligand. So ligands that transfer negative charge to the metal will produce lower coordination number. Example, as I have given you, your anionic ligand, which is already negatively charged, and your neutral ligand. So the anionic, because it will transfer more charge, your metal can only accept fewer of such ligands compared to the neutral ligands. I don't know why it's. So we look at the geometry of your coordination compounds. I'm sure we know most of this geometry. Your M here represent the metal, while the L represent the ligand. So for your Ml2, that is your linear geometry, which we saw in silver, coordinated to your ammonia. For your Ml3, that is trigonal. For your Ml4, that is tetrahedral, or what we call the square planar. For the Ml5, that is your trigonal bipyramidal and square pyramidal. And for your Ml6, that is octahedral. So these are some of the coordination shapes, or what we call geometry of your coordination compound. So for coordination number of 2, the most common is your copper 1, and your silver 1, and your mercury 1. So if you see here, this is our copper 1, and this is our silver 1, because it's 2 minus 1, which is going to give you copper 1, and this is silver 1. And they usually exhibit the coordination number of 2. And coordination number of 2, what kind of structure is that going to be? That is going to be linear. Now for your 3, also your copper 1 will also exhibit your coordination number of 3, that is trigonal. So we have 3 minus 2, this is our copper 1. So that is your trigonal planar structure. So for coordination number of 4, we have 2 types. We have the tetrahedral and you have the square planar. So this is the structure of your square planar, and this is the structure of your tetrahedral complex. And most of your square planar is usually your platinum and your nickel, because they have 8 electrons in their d orbital. They are usually the d8 electron metals. So they usually exhibit your square planar. It's actually because of their splitting pattern. That is why they exhibit the square planar. I will not want to go into octahedral and tetrahedral splitting and the square planar splitting, but just know that because of the splitting pattern, you do more of that when you get to 200 level and the 400 level, for those of you in chemistry. So that is when you actually, this is 200 level. Yes, we are going to, when we get to the other part of my course towards the octahedral and tetrahedral splitting, we are going to see why your square planar why your d8 electrons usually exhibit square planar. So, but just for now, we just know that we are still going to go deeper. So for your coordination number of 4, we can have tetrahedral and we can have square planar. And for coordination number of 5, we say we can have trigonal bipyramidal. So this is the structure of your trigonal bipyramidal. So this is square base. They are all trigonal bipyramidal, but we normally say this is square base, because if you look at the structure, it's a square. These are square base and these are trigonal bipyramidal, but they all contain 5 ligands and 5 donor atoms. And for coordination number of 6, this is actually your octahedral complex. So for donor atoms, 6 donor atoms coordinated to your metal, this is actually your octahedral complex. Any question before we go on? Let me unmute you. Any questions?
Yeah, ask questions.
Sorry, ma, please, when I'm dropping slides.
When you people stop disturbing my class.
Hello, ma.
Ma, sorry,
Yes, I
ma,
can hear
please,
you.
ma, but we need this.
Ma.
Yes. Ask your question. Somebody is calling ma.
Hello, ma.
Yes,
How do you got the structure of that square planar from? Hello, ma. Can you hear me, ma?
I can hear you. Square planar. Okay, this is square planar.
Okay, ma. I said out from the trigonal planar that you said when we have ML3. How do you get the square planar?
When you have what? When you have what? Square planar.
When you have a geometry of ML3, how do you get the diagram, the structure?
ML3. This is ML3 now. Have you seen it? This is trigonal planar. Are you see? Can you see it? Hello?
Yes, ma.
So this is your trigonal planar.
Yes,
This is your ML3. This is your ML3. Are you okay now?
Yes, ma.
Yes.
So how
Don't be telling me. And there are many.
can you can they keep quiet? So any other question?
Even they will want to just
Any
talk and
other
see what they are
question?
doing. It's a new thing. Meanwhile, these things are happening.
Excuse me, ma.
Yes.
No, ma.
Is it Mercury 2 or Mercury 1? Because when you were talking,
Eh?
that has
Mercury?
the coordination power of 2.
Mercury 2.
Okay, ma.
Copper 1, silver 1, and mercury 2.
Okay, ma. Thank you.
So how do I get the slides across?
I don't want to be telling you what you are doing. You just go and be telling me how to leave.
How did Dr. Abdul Wahab said? Has she given you slide, Dr. Abdul Wahab?
No, yeah, but you can put the slide on LMS, ma.
No, ma.
Okay.
Ma.
Are you people logging in from LMS? Did you log in through?
There's nothing on the platform LMS.
Yes, ma.
Hello.
The mic is muted. How we logged in, there's nothing on the LMS.
Okay, I will post it on the LMS. Is that okay?
Yes, ma'am.
Okay, I'll post it on the LMS. So I will meet you again when you are done with Dr. Abdul Wahab. I only took you this week because she's not around. So I will see you when you are done with Dr. Abdul Wahab. Is that okay?
I just said it to you now.
Okay, so see you. Bye-bye.
Bye.
Section what is that profession, madam? 0 308.